Doctor,
Yes.
I have very fast question in the last slide we did in the last video.
Yes, this one.
Yes, we were talking that this, the Newton-Raphson method,
Yeah.
the open method, they converge fast. But here we said that it has slow convergence.
Okay, look. Yes, I understand what you mean. Look, in general, when they converge, they will be fast, except in case you have this types of behavior in your function. In case you have a lot of slope changes or presence of inflection point or region where f prime is much smaller than f second, then you have two possibilities, or slow convergence or divergence. Okay? But when the behavior of the function will not include these, and if you go back to the sorry, if you go back to the example given here, when we started, so this function, this behavior is typical for Newton-Raphson method. So I don't have a lot of slope changes, I don't have inflection points, I don't have critical point where I tend to have f second over f prime, f prime near to zero.
Yes.
So in this case, the convergence will be very fast. Okay.
Doctor, and
yeah.
Sorry, specifically in this slide, I found that the function to be quadratic is worse than being a linear. يعني إذا هذا القسم اللي من تحت إذا بتجلسيه دغري فينا نوصل للسوليوشن من التانجنت.
No, look, what we mean by linear method, if you use the bisection method, let us try here. If you want to use the bisection method, okay, in the bisection method, nearly you have linear variation of your error. Okay, so if you use the bisection method here in this example, first you will start with this interval. Let's say you need a second guess. So let's say your second guess is here, for example. Okay. So if you want to use the bracket technique, the bisection method, first you will get, this is your first iteration, let's say. Your second iteration will be between these two, okay? So nearly, let's say here. Then when you continue, هون you are already very close, بس the bracketing technique will continue. يعني حترجع بعد عن السوليوشن لأنه we have seen إنه sometimes بالbisection method I can be once very close, at next approximation حأرجع بعد لأنه here the root was very close to center. So if the criterion is not satisfied, you will continue. حتحط again a new iteration here, and then between this point and this point a new iteration here. You need here in this example, maybe the bisection also is doing great, okay? But to see it clearly, you should take an example and do the calculation. And this is what we will do here. I will give you a function, an example of a function, and we will use Newton-Raphson, we will use bisection, we will use false position method, and we will see that in some functions, Newton-Raphson will be much more fast. Okay, it will be faster. So again, Karen, it will depend on the function I am considering. Okay, and
yes.
But in general, when it will start, I told you when it will behave in a good way, and you can know it from just from 1 to iterations. If you get a small error from the beginning, then expect that convergence will be very fast. If from beginning you have a large error, then here you have two possibilities, or slow convergence or divergence. So this is why, in case you obtain from beginning a very high error, you can say, no, I will not continue with Newton-Raphson. While if you already from first iteration obtain a small error, you say, I will continue and I will expect the convergence to be very fast.
دكتور سوري سؤال هون انا فاهمه من اللينير انه بدل ما تنزل هيك الجراف بتضل راحه انه ما يكون في هيدا السلوب اللي نازل لتحت.
انت قصدك you mean اذا هي linear curve. No, انت وقت نقول الفاريشن is linear للايرور ما خص الفانكشن، مش انه الفانكشن linear.
لا not the error. انا what I meant exactly.
Yeah.
Okay. Let's start from the red point. هيدي الكيرف ماشي وعم تنزل نزول، اوكي؟ هلا تخيلي كيرف ما عم تنزل نزول، عم بتكمل بطريقه انه ما تنزل كثير لتحت.
هيك؟
اعلى شوي. اعلى.
Like this.
خلص أنا on WhatsApp
We can yes, send me it by WhatsApp. Draw it.
كما ياخذ وقت. Yes, Dr.
Okay. Okay. So now what we will do here, we have introduced the Newton-Raphson method. We will introduce another method that also is an open root method. But before doing this, okay, just let us remember what was the main issues. So we said that in Newton-Raphson method, it's an open method that in which convergence is not guaranteed, okay? But in general, when you obtain a small error at a certain iteration, you predict that convergence will be fast, except for the case where, as I told you, you have changing slope, you have inflection points, or you have points, critical points where f prime is close to 0, okay? So now, let us see now another method, and we will compare in one example all the methods that we introduced together. Another open method is the secant method. What do we mean by it? So you will see here that this method is very similar. So it has similar aspects with Newton-Raphson method, and also it has similar aspects with false position method. And the whole idea here is we will see what are the main similarities and what are the main differences with the other methods. So here, instead of taking one initial guess and drawing the tangent line, what we will do is that we will take 2 points, 2 initial guesses. If you remember, I told you that in open methods, we can have one guess, which was the case in Newton-Raphson method, but also it's possible to perform 2 guesses. But what is the main difference with bracketing technique? That these 2 guesses should not bracket the root. They can be in a way to not bracket the root because it's an open method. So this is what we are doing here. This is the root. We start by 2 initial guesses that are not bracketing the root. And the technique will consist on just joining the 2 points. And then the intersection with x-axis will be the new estimate of the root. So this is, for example, here, this is my first estimate. This is xr1. After first iteration, this is my first estimate for the root. Now to proceed, how I continue? I read the corresponding f. So I take now this point, and I will say now my new 2 points will be this one and the one just before. Okay, so this is x0 here. This is x1. Now, when you compute xr1, this is x2. So now you will work with x1 and x2. You will join the 2 points. The intersection with x-axis will constitute your second estimate of the root. So this is xr2. Now to proceed, you find what is the corresponding point on the graph. Okay, so now you will continue to iterate between now these 2 points. So now all you have to do is to join point this point and this one. Okay, so this is your new line. Now you obtain a third estimation of your root. So this is xr3. As you can see, you are approaching. So here also it seems it's a good method. It's approaching the root. So now if you continue in the first iteration, will be very close to the root, because now you will take these 2 points and you will join them. The intersection now is nearly very close to the root. So in 4 iterations, you will be able to approach your solution. اوكي
دكتور هون الايرور لازم يعطوني اياه ترو ايرور ولا فيني جيب على
لا هون approximate error لانه look انت you do x0 x1 هن initial guesses of the root. اوكي فاكيد يعني يمكن you will not be very close او اذا ثابت you are close it's fine. كيف how you calculate the approximate error? When you calculate x2 x2 you compare it with x1 بيرجع this will be your approximate error. When you calculate here x3 اللي هي the second estimate of the root, then you compare it with x2. The approximate error will be by comparing a new point with respect to the old point just before. Okay?
Yes.
Okay. هلا we will see it in an example. Let me check the questions. Okay. So Let us see in an example how we do this. So here you can find the general procedure. The general procedure is very similar to Newton-Raphson method. Just what is the difference, the main difference? As I told you, in all methods consisting of joining 2 points, you will obtain the estimate of xr in this form. So the estimate will be in the form xi minus fxi over f prime xi. But as I told you, the different aspect between the different methods is how you compute f prime xi. In the Newton-Raphson method, you compute it from by using the analytical derivative. So I give you fx, you derive fx, you get f prime x, and then you replace it analytically and you get your solution. While here in secant method, you are using the backward difference method to approximate f prime xi, because you are using xi and xi minus 1. So we can say that Newton-Raphson method is using the exact derivative, while secant method is using the forward difference method to approximate the derivative. And if you remember in the false position method, this f prime was the slope of the line joining the 2 points. Okay, so in all cases it's nearly similar, but the way we compute this derivative is changing. Okay, now so now comparing with the false position method, you have that this secant method is very similar to false position method because it requires 2 initial estimates. So, and we join these 2 points, and the intersection with x-axis is the new estimate of the root. So this is the common between the two. While the difference is that in false position method, you need to bracket the root, while in secant method, you don't need to bracket the root. So you can start from any 2 initial guesses. Okay. Now, what we will do now is to compare with Newton-Raphson method. As we said, the approach is similar to Newton-Raphson, okay? But what is different mainly is how we compute the derivative. In Newton-Raphson method, we compute the exact value of the derivative because we derive the function and we replace at the point. However, in this case, in the secant method, to compute f prime at xi, we are using the backward scheme. Okay, so in general, Newton-Raphson will behave better than the secant method because it will take the exact value of the derivative. But what is advantages in the secant method is that you don't have to find f prime. So let's say the function is complex and calculation and the analytical solution of f prime is not very simple to find. You can use the secant method in this case. Okay. Any question on this?
بخصوص الديريفاتيف، ما انا ما بدي اجيب ديريفاتيف هون.
نعم.
ما بدي اجيب ديريفاتيف هون.
لا، لانه بالسيكنت ميثود بدل ما تجيب اف برايم الفانكشن اف برايم تعمل ريبليسمنت يو سيميوليت اف برايم يوزنج الباكورد ميثود. يعني شو حتحط مطرح اف برايم؟ حتحط اف اكس اي ماينس اف اكس اي ماينس 1 اوفر اكس اي ماينس اكس اي ماينس 1، او هن هون قلبينهم يعني قلبوا فوق بالنيميريتور وبالدينومينيتور حطوها اكس اي ماينس.
اوكي يعني اوكي سوري عم بقاطعك يعني، بس انا عندي هون ستيب زياده بعد، يعني انا تجيب اكس اي بلس 1 مش مزبوط. بدي ارجع اجيب الاف برايم، يعني انا بحط ريبليسمنت باكس اي بلس 1 باف، بجيب اف اكس 1 بلس 1، برجع بجيب الاف برايم اكس بلس اكس اي بلس 1 مزبوط.
لوك انت اذا عم تشتغل بالسيكنت ميثود ما بدك تجيب اف برايم، تستعمل هاي الفورمولا. يعني اف برايم ما بتجيبها دايركتلي، بتجيبها نيوميريكلي. تعملها يعني اف برايم ات اكس اي حتكون اف اكس اي ماينس اف اكس اي ماينس 1 over اكس اي ماينس اكس اي ماينس 1. you don't have to derive الفانكشن الاساسيه. بينما بالنيوتن-رافسون ميثود تجيب الاف برايم ات اكس اي مجبور تعمل ديريفاتيف للفانكشن الاساسيه and to replace in.
فهمت عليك.
اوكي هلا
خلص هلا بس نعمل اكزامبل.
yes it will be clearer in the example. exactly. هلا هون it's backward Why it's backward؟ لأنه to compute أنت بدك f prime xi. To compute f prime xi ما استعملت points I plus 1 و I استعملت points I و I minus 1. This is why here it's called it's the finite backward difference method that is used, not the forward method. Okay. So let me check if anyone has another question. Ghadi, I don't understand. Did you have any question? Okay, خلص.
لا ماشي عم بقول لها ميرسي لكارن لأن جاوبت.
Yeah. So let us do an example. Okay. So taking the first example, we give you fx equal to x cubed minus 3x plus 1. And they gave you two initial guesses, x0 and x1 are equal to 0 and 1. And you want to compute how many iterations are required to reach an approximate error that is smaller than 10 minus 14. So as you can see here, the criterion is very strict. 10 minus 14, maybe you will need several iterations. So let us try to use this method. مثلا, I will give you what will be the difference if you want to use a Newton-Raphson method. So let us do the first iteration here. In the first iteration, I want to compute x2. To compute x2, I just use the formula. No, x2 is x1 minus f at هيدي إذا بدكم هيدي I plus 1 equal to xi, which is 1 here, minus f at 1, so minus f xi, times xi minus 1, so this is xi minus 1, minus xi over fxi minus 1 minus fxi. So here, x2 will be depending on the values at 0 and 1. Okay? So first, what is x1? x1 is 1. fx1, to find what is f at x1, all you have to do is to replace in your function. So your function here is fx equal x cubed minus 3x plus 1. So if you replace I equal 1, you get f at x1. x1 is 1. So if I replace, I have 1 minus 3 minus 2 plus 1 minus 1. Okay? So f of x1 here is minus 1. I replace it by minus 1. I have x0 is 0, x1 is 1. F of x0, to get f at 0, x0 is 0. I just replace x by 0 here. 0 minus 0 plus 1, so f of 0 is 1. So I replace in my equation here fx0 is 1, while fx1 is already computed, it's minus 1. Okay, so now I have everything. I can get the value of x2. So I got that x2 is 0.5. Actually, this is the first iteration. This is my first estimate of xr. But you can compare to the guess, if you want. هيدي الerror in general will be high لأنه أنا عملت حيلا guess. So it might not be close to the root. But I can compare. هن عادة أنا عطوني initial guess x0, x1. I got x2. I compare x2 to x1 and I predict انه maybe the error will be high لانه بعد ما بلشنا it depends on the guess. هيدا النمبر ما كتير بيهمني. I will really start to do analysis after the second iteration. Okay? Now I will continue to iterate. I will now find the second estimate of my root, which is x3. So same formula. Now just now بدل x1 بدي احط x2. بدل x0, instead of x0 I put x1. So x3 will be x2 minus fx2 times x1 minus x2 over fx1 minus fx2. If I perform my calculation, I get 0.2. So this will be my updated estimate of the root. So I compare it with the previous estimate. This is the approximate error. So now the approximate error is by comparing 0.2 to 0.5. This is, and I divide by 0.2, the new value, to find the relative approximate error. I get 1.5. It's a high value. Okay, it's a high value. Now to know what will happen, I will هي high but relatively still acceptable, because now I will continue. If I see that it's decreasing, I am on the safe side. Okay, so in the third iteration, I will get that the error will be reduced significantly. from 1.5 to 0.43871. فبلشت الconvergence تكون fast عندي. So I expect that if I continue, I will converge in a fast way. So I will continue to perform iteration, okay? And this table will compare for me, for the same example, if I start from the same example, using the different techniques, how many iterations I need, okay? So first, if I use the bisection method, I need a lot of iterations. Again, look, the criterion is very strict. This is why I am summarizing in a table, because it will take a lot of time to conclude. But if I give you a criterion that is less strict, you can do it by hand. يعني مثلا if I tell you strive, for example, epsilon smaller than 1%, you can compare the different methods and you will see that which one will converge faster. So here, for example, if we perform the calculations until reaching a convergence criterion of 10 minus 14, we will see that if we use the bisection method, starting with an initial bracket of 0, 1, okay, we will require 54 iterations to find the actual solution, which is really a high number. Now, for if we use let's say the false position method, okay, for the false position method we need two guesses اللي هن هناخدهم كمان 0 and 1, okay. So what will happen is that we need less iterations. How we can explain this? We can explain this if we draw the function between 0 and 1. We will see that my the behavior of my function is not very far from linear profile. So I can expect to reach a good solution in a smaller number of steps. This is why here the false position method allowed me to reduce the number of iteration from 54 to 17, because the behavior of my function is not far from the linear behavior. Now, if I proceed with the secant method, here the secant method is working well. It will just need 11 iterations. Okay, so this is again, we have seen that open roots, when they converge in general, they will be fast. They will have fast convergence. The only condition is that we don't have the main issues that I introduced for you. And we don't have inflection points. We don't have high sloping changes, etc. Okay, high change of
Doctor.
Yes.
Doctor.
Yes.
I expected the opposite, لأنه نحن قلنا مثلا إذا x10 minus 1 bisection ما بتزبط، بس إنه إذا x3 أحسن.
إذا x3 شو الأحسن؟
إنه لأنه الباور هي أوطى فبتكون less بتكون.
هلا هي منا perfectly linear يا كارين، منا perfectly linear، بس إذا بترسميها it's nearly like this. Let's say if you draw a straight line منا كتير بعيدة، مش مثل ما تكون عندك like this، مش مثل ما تكون مثل
أنا هيك قصدي، يعني قصدي إنه كان المفروض أنا تصورتها تكون أقل من 54 iteration، يعني كنت قلت لك إنه البايسكشن منيحة هون.
هلا هي look البايسكشن is not, it doesn't mean bisection is bad، بس انت ليك الاكيورسي اللي بدك اياها. هيدي الاكيورسي كثير كبيره يا كرم. بالبايسكشن بدك تضلي تقسمي على 2 تقسمي على 2، بدك تقدري توصلي لهالبراكت الكثير سمول بدك كثير وقت. مزبوط انه it will converge، اكيد it will converge and it will work well، بس انت because your criterion of convergence is very strict، يعني انت تخيلي انت بلشتي من interval 1، يعني difference between the upper and lower end is 1. انت بدك تروحي ل approximate error of 10 minus 14. يعني تخيلي قد
ايه. يعني اذا you gave us this graph and you told us what method is the best، كيف هون فينا نعرف؟
اوكي هلا عادة الجراف بيساعدك to compare ال false position وال bisection method. اوكي لانه اذا كانت close to linear profile then false position is better. بس كمان وقت يكون الجراف ما في سلوب، ما في كثير تشينجز، يعني هيدا الجراف مثلا اتس سموث جراف، ما عندي طلوع نزول، ما عندي تشينج ستريكت تشينج ان سلوب، ما عندي انفلكشن بوينت، ما عندي بوينتس اف برايم تبعهم تقريبا زيرو. So you expect in such behavior انه الاوبن methods يكونوا more efficient. especially if you consider initial gas يعني قريب من الروot. So when you have a function ما عندها very high change in slope, ما عندها inflection points, ما عندها maximum or minimum, then expect إنه the open methods can behave better than the bracketing methods. Okay?
Yes, thank you.
Okay. Now, we will see another a modified version of the secant method. Okay, as we said, the secant method will take two initial guesses, and each time we update the 2 points. The modified secant method will just start from one guess. Okay, and it will take 1 point. Instead of taking a second point, it will take a certain delta x. So delta x is fixed in the secant method. So if I know 1 point initial guess, I take delta, let's say 10 minus 3 delta is. I consider that the second point can just be found by saying that delta x is equal to delta. So I find what is my second point on the curve, and then I join the 2 points. So it's just the main difference between the modified secant method and the secant method. The secant method will start from 2 points, any 2 points, and then I will update the point. Delta x between the point will not be the same. We will see it back in the graph. While for the modified secant method, it will fix the space between the 2 points I'm considering by considering a certain value of delta. We will look together on the graph to see the difference. If you go back to this graph here of the secant method, so let's say you can, when you did this initial guess between these 2 points, this was your delta x initially, okay? So this was delta x between the 2 points. When you found a new point again, so now your new 2 points are these 2 ones. They will be characterized by a different delta x between them. So sometimes in this way, if they are very far, and if the points are getting farther from each other, I am getting far from the actual derivative, because you know that the actual derivative will be more accurate when points are close to each other. This is why a modified version of the secant method consists of fixing this delta x. In this way, I don't have to do 2 initial guess. I just do 1 initial guess. And once I know where is my initial guess, I do delta x. Let's say delta is 10 minus 3. And of course, smaller is delta, then you are closer to the Raphson method, because you will be very close to the tangent. And now if you take delta minus 3, this is your other point. Okay, so smaller is delta. When you join these 2 points, you will get a closer line to the tangent line. So here it's nearly tangent. It's nearly the same as the tangent, because due to the linear variation of your function here. Now, in the next step, I will have nearly the same point, because as I told you, here the behavior was nearly linear. Now, when I take this point, here the modified secant method will behave better, because instead of joining these 2 points, which are a little bit far from each other, I will say that I will take delta, a space delta, between this point. So this is delta x equal to delta equal to 10 minus 3. And for this delta correspond on the graph this point. And in this way, when joining the 2 points, I will be very close to the tangent. So I am, as I reduce delta, as I am close to the Newton-Raphson method. So this will be my second estimation of the root. So as you can see, the modified secant method can be more efficient, because it will need less iterations to converge. The only condition will be to reduce delta. And as I reduce delta, as I will be close to the Newton-Raphson method. And also in this way, I don't have to compute f prime. And this is an advantage. And if I don't want to calculate f prime, the function, but I want to be close to the Newton-Raphson method, I take delta very small. So when I join the 2 points, I will be nearly, I will have the tangent nearly, and then I can have the solution in a less number of iterations. Okay.
دكتور
Yes.
اوكي نحن انه عرفنا ايمتى نستعمل مثلا الفولس، نسيت اسمهم على قد الاولي والثاني تعلمناهم. اوكي هون انا كيف بدي اعرف اذا بدي استعمل السيكنت ميثود او الموديفايد سيكنت او النيوتن رابسون ميثود؟
اوكي هلا in general مثل ما قلت لك انت if you don't اذا ال f of x very complicated ومنك قادر تجيب ال f prime، هلا in general you can calculate the derivative but sometimes it can be very complex to find it. In this case اوكي اذا منك قادر تجيبها what you can do you will go to numerical technique. فساعتها بدك تعمل السيكنت او الموديفايد سيكنت. هلا الموديفايد سيكنت is more accurate ليه؟ لانه فيك تقرب كثير على الديريفاتيف. يعني انت كل ما صغرت دلتا كل ما قربت على الديريفاتيف الاكتشوال. اوكي؟ يعني اذا بدك الموديفايد سيكنت in general will behave better من السيكنت method. الا اذا انت بدك تبلش ب two initial guesses ب any 2 points and you can start. يعني it always if you want depend on the problem. بدك تشوف انت البروبلم عندك اياه to decide. هلا انا I will give you in general I will tell you use this method but you should know the property of each. يعني you expect انه المodified secant is better because it will behave closer للنيوتن رافسون method اللي هي compute the exact derivative. الا in cases الفيو cases اللي شفناهم. بالفيو cases اللي شفناهم شفنا انه نيوتن رافسون منا effective. ساعتها يمكن احلى لك تجرب السيكنت might perform better لانه السيكنت ساعتها فيها تتخطى مشكله الاكتوال تانجنت لاين. يعني لاحظ هون مثلا if you start if you have an inflection point and you are just doing the tangent كل مره عم بتبعد عن السوليوشن. بينما اذا بتعمل هون السيكنت it might perform better because look اذا بستعمل هون السيكنت let's say this is x0 بدل ما اخذ الاكتوال تانجنت باخذ بوينت شوي ابعد منه لانه هي شو المشكله. يعني اوقات التانجنت هي عم تعمل لي مشكله. يعني whenever you face these problems اللي هن انه في slope changes او في inflection point او في regions with a prime smaller much smaller than a second you can think about بدل النيوتن رافسون secant مش وحتى مش الموديفايد secant. يعني الموديفايد secant كل ما دلتا صغرت بتقرب على نيوتن رافسون. So here it will behave better هيدي الميثود because look بس اخذ 2 points مش كثير قراب ساعتها الانترسكشن مع الاكسس حتكون اقرب على الروت لانه ما بقى مضطر اخذ التانجنت اللي كثير بتبعدني عن الروت. So now this will be let's say your new x. صار هيدا تاني point. Now if you join ال 2 points كمان قربت اكثر على الروت. اوكي يعني السيكنت method might work better وقت النيوتن رافسون method is not working. يعني انا عندي مشكله وقت يكون في slope changes وقت يكون في inflection point وقت يكون في f prime smaller than f second. In case I have these problems ما بستعمل modified او اذا بدي استعمل الموديفايد ما بستعملها مع دلتا very small بكبر الدلتا او بستعمل السيكنت ساعتها. اوكي بس بالبروبلمز يلي عندي البيهيفير اوف ذا فانكشن is good ما عندها slope changes ما عندها inflection ما عندها regions f prime much smaller than f second ساعتها النيوتن رافسون والmodified secant will behave better. Okay. Any other question? If the approximate error criteria is a very small value, we can assume it's easier to use the methods that we know would possibly converge quickly. Yes. Yes, Leia. So if the criteria is very small, okay, you can start, the best way is to start with Newton Raphson. And you can directly know, if you do just 2-3 iterations, you will know how it's going. يعني إذا أنت من أول 2-3 iterations عندك error كتير عالية. So don't expect, يعني this means that أو في divergence أو في slow convergence. بينما إذا بالنيوتن رافسون you got from the 2-3 first iteration small values, then expect that the convergence will be very fast. لأنه مثل ما شفنا last time الconvergence هي is given in Newton Raphson by this equation nearly. فهون عندك إذا بمجرد ما ETI plus 1 طلعت أصغر من ETI then وإذا كان السوسي number smaller than 1 يعني الconvergence حتكون very fast لأنه عم ترجع تعمل square يعني you have quadratic convergence. While in the other case إذا كان value كبيرة you will need more time to converge, and it will be a slow convergence. Okay. So I will open a new session to continue because time will end soon.